My pleasure to introduce Dennis Poshyvanyk from William & Mary, where he's a distinguished associate professor. Dennis has done research in several interrelated areas of software engineering, like software analysis, maintenance and evolution, and requirements traceability. In particular, he works on several aspects of software testing, such as test generation, mutation testing, bug reporting. His papers received 11 Best Papers or Distinguished Paper Awards. That's quite a lot. And maybe you know about these awards called Most Influential or Test of Time Awards, where about 10 years later or 10 conferences later, the program committee picks the best paper from those years. Dennis has a couple of those under his belt. And so Dennis was one of the first researchers to start using deep learning in software engineering research, and he's had his pulse on this trend for a while. And welcome, and thanks for coming to talk to us today.
Thank you very much, Dr. Greenspan, for the introduction. I'm excited to be here today. Can everybody hear me well? Who's on the phone? All right, great. So the goal of my talk is actually to cover 3 topics. First, I will give an introduction what machine learning is, what deep learning is, and why deep learning came to be. And then I will share with you some of the current applications of how deep learning is currently being applied to automate software engineering tasks. And obviously, you've heard a lot about software systems being built today which rely on deep learning. And I'm going to zoom in into some of the software engineering challenges that we need to face while we're developing those systems. So let's quickly jump into machine learning. What is machine learning? Machine learning is the field of artificial intelligence, which essentially allows computers to infer patterns from data, and then we can use these patterns for prediction of new data points. So machine learning obviously is a subfield of artificial intelligence, and AI obviously includes many other areas as well. But I just want to highlight that deep learning is not just a separate field from machine learning. It's a subfield of machine learning for the sake of this talk. So now let's quick look into different types of learning. First type is supervised learning. And in this case, if we have data points, and all these data points have labels, like in this case we have images of strawberries, oranges, and apple, then supervised algorithms would be able to learn some underlying patterns from these images, and when we feed, for example, an orange or a strawberry in this case, it will correctly classify this as a strawberry. Semi-supervised learning or unsupervised learning algorithm, in this case, will not have any labels. So the goal of this algorithm is to actually cluster these images into different categories. So ideally, we would like to place oranges separately from apples and strawberries. Semi-supervised learning algorithm will have some labels for, there is a little bit of delay when I click my pointer, but I hope you will be able to follow me for those of you who joined online. So here we have some labels for some of the data points, but not all. So the idea here is that this algorithm would be able to properly put apples into apple cluster, and if we have some labels, then eventually we will correctly classify apples and apple. And finally, the fourth paradigm or type of learning is reinforcement learning. And the idea here is that it's based on the reward function. And for example, if we're playing a computer game and we pick certain images and we get some points for picking this image, then the reward system will actually promote this particular pattern of behavior. And if we lose points, then it will likely to choose some other pattern. What I wanted to highlight on the slide is we have a number of different algorithms that represent all these different types of learning, and all these algorithms can be actually categorized as canonical representations or shallow representations. And I'll explain what exactly it means in a few slides. However, we do need to have 3 necessary conditions to be able to apply machine learning. First, we need to have a data set. A pattern needs to exist in the data set. If we're dealing with random data, machine learning is unlikely to be effective. And also, condition here is that it would be very difficult to identify analytical formula, mathematical formula explaining a pattern in this data. So this is again the example where we're trying to classify birds and bears, and we're using supervised machine learning algorithm. So here we have the model, which is trying to classify different data points into different clusters. And the moment when we make the wrong classification, obviously we need to tell the model to just the next time we see some image, it would be able to properly classify that in proper cluster. So I will use in this introduction mostly examples related to images, and I'll use supervised learning. However, the same principles would apply to other types of data and to other learning algorithms. So there are 5 necessary elements of the learning process. First, we need to have input. We need to have output. Obviously, we need to have the data and target function and hypothesis. And the target function, this is an ideal function that we're trying to learn to be able to distinguish patterns in a data set. And the hypothesis, this is the function that we're currently learning given the data points. So like in this case, if this is a function that we're trying to learn, once we're feeding the training data into the algorithm, this is our first approximation, this is our second approximation. So this is the evidence that our algorithm is able to learn this target function better. So one thing that we need to highlight is that canonical machine learning algorithms, they don't take raw, like in this case, they don't take raw images as inputs. Typically, they take features as inputs. So all these algorithms rely on feature engineering. And like in this case, if we're trying to classify images, we do need to use features stemming from images. If we're relying on text, we need to rely on features stemming from text, for example, n-grams. And when we are trying to deal with source code, we also need to be able to extract features from the source code, like control flow graphs in this case. So let me give you end-to-end canonical example trying to classify images with a supervised learning technique. So here we have an image, and the first thing to do is to be able to extract features that we will use to classify this image by. So in this case, we can use features like unique colorization, or maybe curvature of an edge, or many other features that we can extract from this image. So these features will be vectorized and put in the vector, and then they will be mapped to this n-dimensional feature space. Obviously, for tasks like image classification, we don't have to do it manually because there are plenty of existing feature extraction algorithms that can help us in this process. However, I would like to highlight that these algorithms have been designed by human experts as well. So when we're talking about canonical machine learning algorithms, one note here is that we are relying on feature or feature extraction algorithms which have been designed by experts or humans. So in this case, once we have all these features, we can put them in this high-dimensional space, we can cluster them, and eventually we can put them in these bags of visual words. And then when we do this for all the images in our training set, we will end up with a vocabulary of all the visual words in this example. And this is something that we will be able to use to classify images. But machine learning algorithms don't take visual bags of words as input. They actually take vectors. So we represent all these features in this vector-based representation. And as you can see, this is a shallow representation. We have a vector representing all these features that we were able to extract from this image. This is an input to machine learning classification algorithm that will start learning to put bears on this side and birds on this side. Obviously, you can see that we're still misclassifying, so this algorithm is still learning. One important note is that if we are relying on these shallow supervised learning algorithms, the best accuracy that we've been able to achieve, for example, on ImageNet dataset containing millions of images in over 1,000 categories, the best accuracy that we're able to achieve up to date is only 60%. And it's nowhere near enough for real-world tasks, mission-critical tasks. There are several shortcomings of these traditional machine learning techniques. First and most importantly, they rely on manually derived features. So these features are typically derived by experts, researchers, or practitioners, but they rely on human expertise. These techniques are not always great at distilling these complex kernels of functions, capturing underlying patterns in the data. And one reason behind that is that they're based on shallow representation. So sometimes it's pretty hard for these algorithms to to model complex features present in the data. So this is exactly where deep learning comes into play. And I just wanted to highlight the main difference between deep learning algorithms and classical machine learning algorithms. This is the way they represent the feature space. So deep learning in this case relies on rich hierarchical feature embeddings versus shallow representations as compared to traditional canonical machine learning approaches. So deep learning has been so popular in the recent years that now we can see proliferation of algorithms for all type of learning. So things in red, these are algorithms, deep learning algorithms, which have been designed for different types of learning. Also, let me give you a very quick introduction what deep learning techniques are, because they are based on the concepts of neurons and neural networks. So in the simplest form, we have a neuron, and we have inputs to this neuron which come from other different neurons. And basically what we do, we take the signal from each of these neurons, we multiply it by unique weight, which represents the strength of the signal, and then we pass it through an activation function in this neuron. And in this case, we are relying on rectified linear unit activation function, which basically decides whether to keep this signal at 0 or just copy the value. And also we have the bias, which typically we use to control the effectiveness of learning. And then when we put this into the networks of neurons, other neurons, we get neural networks. So the idea behind neural networks is that if we're trying to, for example, classify handwritten images, once we train this neural network on hundreds of thousands of different images with labels, what we expect this neural network to do is to eventually distill some of these features that the network will use for classifying these images fully automatically, okay? As compared to shallow or canonical machine learning-based techniques, which actually rely on manually specified features. That's the main difference between canonical and deep learning techniques. Like in this case, you can see that each neuron represents some feature it captures after learning. Although it's very hard to say what exactly that feature is doing, and I'll get back to that issue a little bit later, but that's the basic idea behind deep learning techniques. So the main difference is that we're able to extract features from the data automatically. We can do this for source code using, for example, graph-based neural nets. We can also do this for natural language using recurrent neural nets. We can also use it for images, for example, using convolutional neural nets. So there are different architectures and representations to deal with different types of data. So how exactly do neural nets learn? So one way they learn is actually to rely on the actually error that we can compute at the end. So like in this case, if this is the image that we feed into the neural network, and at the end it classifies it as a bear, basically what happens is that we compute the error because it's this was a misclassification, and then we go back and adjust the weights in the network based on this misclassification. We're trying to actually adjust those weights that were mostly important for this misclassification. So this is an optimization problem. So in order to be able to do that, we are relying on techniques like gradient descent, batch gradient descent, stochastic gradient descent, or mini-batch gradient descent. In this case, it relies on a batch of data to compute an error to be backpropagated in the network. So again, this is end-to-end example of how we're using, in this case, convolutional neural net to classify the image of this bird. Essentially, the image of this bird will be represented as an array of matrices or a tensor. So we're going to apply the kernel to this to each of the matrix, and eventually, what will happen? Each of these layers will extract unique features which will be relevant to the information that we extract from this input, and the weights will signify importance of these features that we're able to extract from the input. So in the end, we will perform the classification, and bear with me. The animation is extremely slow for some reason. I guess it's because I logged into WebEx, and apparently it's not handling my animation well at all. I've actually prepared all the slides statically, but still it's not able to handle even that. So we're waiting We are observing this magic in slow motion, how neural network is able to learn. So eventually it will happen. Eventually it will happen. So I get into classification. So here we see that we misclassified this image again. So we are saying here that this is a dog, but this is a bird. Obviously, probably we don't have good weights yet. We need more training examples. So what we're going to do here, we're going to calculate an error according to the gradient descent, and then we're going to backpropagate this information in the network to adjust the weights, so that next time we see a similar picture, hopefully we'll be able to correctly classify it as a bird and not as a bear. So convolutional networks have surpassed human accuracy for the tasks like image classification. Some of the nets have been shown to achieve 99% accuracy on tasks of image classification. So obviously, this is a very significant improvement over canonical machine learning techniques. So obviously, deep learning does not come with free lunch. However, we do have very significant advantages to using deep learning. For example, it doesn't require manual feature engineering. And this is the most important point why deep learning is picking up, because if it's able to learn features better than experts and then give us much better results, we can actually effectively use it for many of the tasks. Also, it's capable of learning rich hierarchical data representations and can be trained and deployed back to end to end. Of course, there are disadvantages. It does require massive data sets to function effectively. It's also computationally expensive to train, and the models can be sometimes very difficult to interpret. Sometimes we can't or we don't really know what is going inside those layers. So with this basic background, let me quickly jump into a couple of examples of how deep learning has been used to automate software engineering tasks. And let me start here with one of the most common tasks that developers do on a daily basis. They change code. They change code all the time. They change code to correct problems, like in this case, they didn't check for null before adding element to the list. So this is corrective maintenance. Or in this case, they decided to change the signature or return value for the method. Or it may be just perfective maintenance, where we decided to add java.comments. Or perfective maintenance or preventive maintenance, where we decided to find some potential latent bugs and fix them before we actually find them in deployment. So developers do lots of code transformations on a daily basis, and lots of these code transformations are stored in open source repositories. Nowadays, we can find millions, potentially billions of changes stored in GitHub or GitLab like repositories. So obviously, this has been a very good opportunity for software engineering researchers to use this data to support or automate some of these software engineering tasks. And this has been a long-standing goal of software engineering research for a while. However, there are many approaches that actually rely either on heuristics or handcrafted rules or human expertise to take advantage of this data to solve some of the problem. What we're trying to do in our research is actually to learn from this data fully automatically without much supervision. For example, without specifying which particular features from the code should be considered for learning. And we like to be able to do this for hundreds, thousands, or potentially millions of changes which happen in this project. And once we train the models on this data, we would like to be able to apply them for real tasks. So that's the overall goal. And for the next couple applications, I will be relying on neural machine translation. This is a supervised deep learning-based approach. And the idea here is that we would like to train this model on samples of the code before and after code modifications. So the idea here is that once we find lots of pairs like this, potentially millions of pairs of code changes like this, then we should be able to feed to neural machine translation approach either in the code before and get the after version, or after and get before, or glean some useful patterns that could be used to generate these transformations automatically. Neural machine translations has been exploding for tasks like language translation, text summarization, question answering, or conversational modeling. And at the very high level, neural machine translation is represented as an encoder-decoder architecture, which consists of two recurrent neural nets, which are trained jointly. And typically, it also has attention mechanism that helps to align target with source tokens. Now let me actually go to the actual task that we apply neural machine translation for, and this is a task of mutation testing. And the idea behind mutation testing is to be able to guide generation of test cases or evaluate the quality of the test suite. So the overall idea is that if we are developing the program and we have a test suite, we would like to know how good this test suite is, right? So if we make a mistake in our code, and if our test cases don't fail, obviously this is less than ideal, right? In that case, that bug may propagate to production, right? So ideally, we want to make sure that we have good enough test cases that will catch all sorts of mistakes made by programmers. So in order to enable this evaluation, mutation testing is frequently used. Like in this case, there has been multiple mutation-based frameworks designed for different programming languages, and they use all sorts of different heuristics and handcrafted rules how to mutate the source code to check effectiveness of these test cases. So in this example, for example, we can use increment mutation operator that will find an increment in this piece of source code. Then it will decrement it, obviously introducing a bug with different behavior in the method. And then we would like to see if our test cases are able to actually catch, or in this case, fail, because that would be a good thing, because we would be able to hopefully track down the bug. So in this case, mutation testing practice and research mostly relied on potential bias, because the way these operators are designed are mostly relying on human expertise. In many cases, we may be relying even on missing information, or it's not even clear whether those mutation operators are representative of real bugs. And we have first-hand experience designing a mutation operator for Android applications, and we spent actually several long months looking over 2,000 software artifacts, trying to come up with a set of comprehensive mutation operators for Android. And I can confirm firsthand that this is time-consuming, error-prone exercise. Okay? We don't even know if we ended up with a complete list of mutation operators. So the idea behind this research is to be able to infer these mutation operators fully automatically from the actual changes available in open source repositories. And once we infer or learn these underlying mutation operators, we would like to be able to apply them in the real code, right? And we would like to instantiate relevant and meaningful mutation operators given the code context. So this is the task that we're trying to solve with neural machine translation in this case. Imagine that we have a version of the code. This is a buggy version of the code, and this is a fixed version of the code, which we can get from, in this case, version control system. If this is a bug fix, and we are thinking about translation in terms of going from the fixed code to the buggy code. Okay? So I would like you for a second to this information to sink in. We are going from fixed one to the buggy one, right? Because we would like to take a clean version of the code and generate a bug in that version of the code, right? So that we can actually check if the test case can detect that bug. So this is essentially how we train our neural machine translation model. This model, again, relies on a set of steps. First, we're mining these bug fixes from open source data. Then we represent these transformations as pairs. Then we'll abstract this code. I'll explain why in a second. And then we train neural machine translation model to be able to do this transformation. So in this case, we're mining millions of commits from GitHub repository. And for the sake of this work, we are just relying on Java commits because we're doing this for Java programming language for the sake of the study. And after that, we are differencing every single file before a buggy version and the fixed one to identify the actual changes that happened in between. So since source code is actually not constrained by any vocabularies, and those of you who looked ever into source code, you know that developers are very creative in terms of coming up with names for identifiers, classes, and methods. And unique vocabulary for source code can surpass English vocabulary by orders of magnitude. Okay, and this is a problem, obviously, for neural machine translation approaches, since they produce probabilities for all the words. So in order to deal with vocabulary problem, we actually abstract the code by essentially replacing identifiers and literals with typified IDs, like in this case. So we take this piece of source code and we abstract it using typified IDs. We also keep Java keyword separators and some of the frequent idioms that appear in the code. And the idea here is that we, for every pair of source code for buggy and fixed one, we take this code, we abstract this code, then we feed each pair of this code fixed to buggy abstracted version to neural machine translation approach. And then when we have an input to the engine, essentially it generates an abstracted buggy or mutated version of the code that we can instantiate in real code using some of the mappings that we preserve. So just to give you some idea how well this technique works in this setting, we computed several metrics. I'll just give you some snapshot of these results. So perfect prediction essentially gives us those cases where we feed the buggy version of the method and we feed the fixed version of the method and actually get the buggy version of the method. So we actually get the real bug for that method that we feed into neural machine translation algorithm. The bad prediction, this is the one that just copies input to the output. Obviously, we want the model to be able to mutate it. And mutated is a version where model mutates the code, but it doesn't necessarily correspond to the perfect bug. Still, it's a valid mutation. It just doesn't correspond to the perfect bug. So we've looked into general models that use all types of AST operations, and they're able to generate up to 21% perfect predictions and 52% for mutated predictions. So overall, they're able to mutate approximately 73% of inputs, and specialized models can actually do this really well for certain clusters of AST operations. And most importantly, the code that mutation engine based on neural machine translation generates actually is able to generate syntactically correct code in almost 97% of the cases. So the model is able to learn syntactically correct code, which is fairly impressive. Here, I'm just giving you some examples. The first one is a perfect prediction generated by the general model. I just want you to quickly look at this code and see that some of these mutations are not trivial. So the model is able to generate and learn fairly complex mutations. Okay? So now let me go into one of the most difficult problems that we're facing in software engineering, and this is automated program repair. So the main goal behind automated program repair is to be able to find the bug and automatically fix it. Okay? And obviously, if we're able to do that, some of the programmers might be out of job. But good news is that we're nowhere near solving this problem fully. But deep learning is helping greatly in terms of making significant progress towards that. So the basic idea behind automated program repair, we have a program with a bug. And then obviously we have some test cases which are potentially failing because of that bug. We have some fault localization technique which may actually use some information from those failing test cases. And then we have this buggy code, and in the middle we have this approach which is trying to generate a patch to fix this bug. And then we generate a candidate patch, we run test cases. If they pass, we say we likely solve the bug, so we deploy the patch. If we still have failing test cases, then we try to generate this patch again. And I just want to highlight that we have a number of program repair techniques which came out of the research community. However, many of those techniques are still relying on handcrafted rules and heuristics, how to come up or design these patches. And again, the premise of our research is to be able to do this fully automatically without telling the machine what it should consider as far as changes, as far as code, to be able to automatically learn this pattern without any handcrafted rules, without predefined operators or locations. And in this case, we also wanted to decouple it from test cases to be able to repair the code without any knowledge that we can potentially glean from test cases. So in this case, we're also relying on neural machine translation approach, but we are going the other way around. We're training the model to learn of how we actually go from buggy code to the fixed code. Okay, it's a little bit more natural in this case. So in this case, again, we're feeding hundreds of thousands of pairs of code that we find in open source repositories. we also represent these transformational pairs, we abstract them, and then once we feed a buggy code to the model, we would like to see if the model is able to fix the buggy code. So in this case, we're trying to generate multiple patches because there is no guarantee that neural machine translation will generate the correct patch in the first attempt. So in this case, we're actually relying on beam search, which tries to keep multiple concurrent hypotheses. In this case, you see an example where the beam search is keeping 3 concurrent hypotheses until it generates or reaches the end of sentence. And those are going to be 3 candidate translations proposed by the beam search. These are just some preliminary results that I wanted to share with you. So basically what you see on these graphs is for beam search of size 50, we are able to fix approximately 50% of the bugs for small methods. And small methods, these are methods which contain up to 50 lines of code. So if we feed a small method, which is up to 50 lines of code containing a bug, this technique was able, with beam search size 50, was able to fix it in 50% of the cases. When we look into the actual numbers, then you see that we were able to fix almost 3,000 bugs. 3,000 bugs from the wild, from hundreds of open source projects. So these are not curated, carefully chosen benchmarks of just a few projects. These are hundreds of bugs from hundreds of different projects in the wild that we were able to fix fully automatically by relying on neural machine translation. In this case, obviously, by considering 50 candidate hypotheses, but still, even if you have to consider 20, we get 43% of bugs fixed fully automatically. For small. So synthetic correctness was not bad at all. So this technique was able to produce even in the worst case, 82% syntactically correct code for the fixed version of the file. Okay? And by the way, one thing which I wanted to highlight, this is the most conservative estimate of how well this technique is able to do, because we are talking about perfect predictions. So this means that this neural machine translation technique was able to guess the perfect fix. And the perfect, we mean, this is what we found in version control system. However, some of these fixes, as we looked into the results, were still meaningful. We just couldn't measure that automatically because we're dealing with thousands of bugs. So actual percentage in terms of valid patches is higher than the number that you see here. Okay? I think that's important because the technique is actually more powerful than the numbers show. Also, these are some qualitative examples of how fixes look like. Again, as you can see, the first line is the buggy version, and the second one is a fixed one. Some of these fixes are far from being trivial. They involve adding new method calls, changing statements, changing logic in the program. So we can see that neural machine translation is able to learn fairly complex patterns. Now, let's look even deeper into what those complex patterns are. And this is one of the papers that we're actually going to present in May at ICSI. We actually trained this model on actual pull requests. Okay, and pull requests, those are changes which have been reviewed and approved by developers. So those are meaningful and high quality changes which have been made on open source systems, as opposed to some commits which may or may not contain just fixes of a particular bug. So what we've done, we actually deep dived into the data and we tried to understand what kind of changes the model is able to learn and perform. And roughly, we classified all into 3 categories: bug fixes, refactorings, and other changes. So as far as bug fixes are concerned, we did find that it's able to learn changes related, for example, to exceptions, removing thrown exceptions, adding try blocks, changing exception types and catch clauses, adding null checks, changing method return types, removing synchronized blocks. When it comes to refactorings, it was able to learn non-trivial refactoring as well, such as refactorings related to inheritance, method interactions, lots of refactorings related to improving readability of the code, naming conventions, encapsulation, as well as a slew of all other changes in this case. So as you can see, these type of changes are far from trivial changes. So let me give you 2 specific examples. This one example, the source code on the left is the one which was before the change, and the code on the right, this is what the model was able to generate. So basically, the logic here is that the model took this anonymous class and it refactored it into a lambda expression. And that's exactly what the Java developer for the overt system did as part of the change. And this was done as a part of transition to Java 28. Okay? So this is one of the very impressive examples of the change that the model was able to do. Also, in this case, the model was able to take these two catches and put them in one place. So obviously, I would rather prefer this version for readability purposes. Okay. Now switching gears just a little bit, let me show you what we can do deep learning using other modalities of the data. And the problem that I would like to illustrate here is actually the one where we build mobile applications. So as some of you might know, when we build mobile applications, graphical user interface is extremely important, right? And all of us, I'm sure, are demanding users. We want high quality user interfaces to interact, right? So basically what happens, these companies have two separate teams. They have graphical user interface designers. These are typically brilliant designers who know how to use Photoshop. So they sketch great interfaces, and then they push them to the development team who's supposed to implement these interfaces into working apps. And when you look into the reality, into this problem, there is a lot of feedback going back and forth, because sometimes developers make mistakes. They go back to designers again suggest changes. So it's a never-ending loop. So what we're trying to do in this case, we're trying to fully automate this problem outright to get the screenshot of the sketch of the graphical user interface and automatically generate the code, or at least a stub code for this Android application. So that's a problem that we're trying to address here. The resulting solution is fairly complicated, and I'm not going to go into all the details because it relies on multiple techniques from mining software repositories, dynamic analysis, computer vision techniques. But most importantly, I would like to highlight the deep learning component in the solution plays a critical role, because in fact, I'll show you the numbers. Without deep learning, this solution would not work at all. Okay, and roughly speaking, this solution is comprised of 3 steps. First, we take the image. We use computer vision techniques to identify bounding boxes of likely components on the screen. And then the second important problem, and this is where deep learning comes in, we actually need to properly classify those components on the screenshot into actual types of Android components, so that we're able to generate actual application. Okay, and if we don't get those types correctly, we're not going to generate the correct application. So the main question, or million-dollar question here, where does that training data come from, right? Because that's where deep learning strives. We need to get a lot of training data. So for this purpose, we are relying on mining software repositories. We are and dynamic analysis. So we're getting hundreds, in fact, in this case, we got 10,000 Android applications from these repositories that we are able to automatically execute on a farm of devices and in our lab. And we're executing each and single of these applications automatically using systematic exploration techniques. And while executing these applications, we are taking screenshots of these applications, and using tools like UI Automator, we're also collecting all the information about the screen, what kind of components on the screen, types of these components, as well as other metadata. And then we are able to crop basically each component that shows on the screen, match it with information from the XML, and this way we can generate hundreds of thousands of data points that come from real applications. So this is actually used as an input to deep learning techniques to classify component types. So just to show you, if we are to rely on classical machine learning technique to do this task, the best classifier, in this case, this is a support vector machine, which is based on bags of visual words, gets us to 65% accuracy. Okay? This is kind of nowhere near in terms of what we need in order to generate correct applications. So while using deep learning, in this case we're using convolutional neural nets based on Alex architecture, we are able to get 91% accuracy. So this is a fairly significant jump in terms of accuracy. And we were able to evaluate this technique with some developers from Google and Facebook who were quite positive about initial results. They basically really like the fact that you can just throw a sketch at the approach that can generate a lot of boilerplate code fully automatically. Also, they gave us some useful suggestions for for future work, but overall we got fairly positive feedback that tools like this would be needed in real development pipelines. So here I'm showing some examples of which were generated by redraw. This is a screenshot that was fed to redraw, just a screenshot, and this is a screenshot of the actual application generated by the approach. I'm not going into details how we actually generated the approach. I can talk about that offline, but that's basically the result. Of course, there are some minor differences, but in these cases, we don't have any major misclassifications. So our resulting application looks very similar to the original screenshot. So now, let me switch to another problem. And this is a problem of building real software systems that contain deep learning data. Okay, and this is becoming a bigger trend nowadays. So I would like to start this with a quote from Director of AI at Tesla, Andrei Karpathy, who basically says that neural networks are not just yet another class of things, but they represent the beginning of a fundamental shift in how we write software. And Karpathy refers to this as software 2.0. So let me quickly explain what he means by this. In traditional sense, in our classical situation, when we write a program, it's a set of instructions, right? We compile the program, then we feed the data into the program, we run it on the computer, and we get an output, right? And that's how we've been solving problems for many years, right? We've been writing solutions this traditional way. Karpathy argues that if you actually have a lot of data, right, and for example, you're solving a task like image classification, instead of writing this algorithm manually, you can actually rely on deep learning to produce a set of instructions that will be able to solve this problem, given that you have a lot of data and examples and labels on how to solve this problem. And the problem with this approach, or rather the challenge with this approach, this is our software 1.0. This is the software that we're used to, right? We understand what this code does, right? We look at the code, we understand what this code does. And this is software 2.0, okay? And these weights here, millions of these weights, sometimes billions of these weights, depending on the model, this is the knowledge of this system in terms of how it's performing its task. So why is deep learning software 2.0? Basically, the idea here is that if this is a program that we can write manually, maybe it's going to be suboptimal program. But if we have a lot of data in terms of, and if we can train the model, then perhaps this model can find a much better program and write the program for us, okay? Solving that particular problem. And indeed, we see software 2.0, or in this case, systems which are relying on deep learning for solving certain tasks. Pervading certain industries, we see that deep learning has been used for tasks like image recognition and understanding, also speech synthesis, and many other tasks, including natural language translation. So the vision here is that if this is our software project, 1.0, eventually some part of this project will be subsumed by software 2.0. And this is a part of the project which relies on deep learning to accomplish certain algorithms, okay? If, let's say, we have a software for self-driven cars, then maybe this is a component which is going to be responsible for recognizing lanes or stop signs or other road signs. But we also have other software which traditional programmers write. And as deep learning evolves, we're probably going to see more and more software 2.0, or software which is written with deep learning techniques, instructions written with deep learning techniques in software projects. However, if we look into what a system with deep learning looks like nowadays, the picture is going to be something like this. And this is a figure that comes from Google researchers who actually looked into several of systems that rely on deep learning. They say that amount of code or machine learning code in this system is usually only 5%. The 95% of the code is actually packages and the glue code, which is written around it to support the underlying infrastructure. But the tricky part, obviously, and we can take it into discussion, that even though this is 5% of the code, once we build these models, this is where the actual challenges and problems are, because those problems pose certain challenges for development and maintenance. So when we try to look into software development process, and this is how we've been building software systems over years, if we are to build software systems that rely on deep learning as the underlying components, the process is likely to change because we have other software process stages, like in this case, we also have data collection, we have data labeling steps, we have data preparation, model learning and integration, model management, and these are all tasks pertinent to building deep learning-based components that may be part of software systems. So essentially, the idea here is that as we start building these systems relying on deep learning, we're going to see more and more developers concerned with tasks like data collection, data curation, data labeling, model building, data verification, so forth and so on. But we're still going to see a lot of glue code, at least for the near future, being written and maintained by developers in the software 1.0 sense. So now the major question: what kind of challenges do we actually observe in the development of these deep learning-based systems? So let me jump into some of these challenges. Software development challenges. The first one is I'm waiting for the slides to show up. There is a bit of lag. The first one comes from a fundamental paradigm shift because we are programming these systems by relying on the data. So essentially, the data programs these systems, right? We're no longer writing instructions. We're feeding the data to the models to train these models. And obviously, this creates certain challenges because we cannot even reason about some functional, even some non-functional requirements until the model is trained, right? Until we know what accuracy we can expect from the model. So in this sense, effort estimation also becomes very, very challenging problem, right? Because it's hard to predict anything until we know what we're able to do with the system. Experiment management becomes another significant problem because if we're trying to solve, for example, the problem of stop sign detection, and we are building and training the model for this problem, we will have so many parameters to worry about to build the best possible model for this task, right? And in order to accomplish this, we're going to train hundreds or thousands of different models, right? And while doing that, we're also going to be collecting training data from other different sources. So managing these experiments, managing experiments while the data changes, or versioning these experiments and data becomes a pretty significant problem. Also, we have issues related to data labeling. And if you thought that this is a trivial task, maybe it is a trivial task for, let's say, lanes from this example. In this case, we can easily label these lanes, right? Because that would be actually the input to our deep learning-based algorithm. Some of these samples with actual labels. And in this case, as we can see, we were able to train pretty good classifiers. It's able to detect these lines fairly accurately. However, let's look into some corner cases, right? Do you think it would be easy to label something like this, right? Then we start running into problems. How exactly do we decide what is exactly the lane in this example, right? So, of course, we can provide lots of useful tools to developers or people who would be actually involved in this data labeling. And of course, we can also put some intelligence into these tools that could actually take advantage of some of the existing data in our set, which has been labeled. But there is quite a bit of research that is happening in that direction. Also, versioning models becomes a pretty significant problem. As I said, we have fairly complex experiments involving multiple models, multiple parameters, multiple versions of the data. Versioning all this becomes a significant challenge. When it comes to maintenance, we also have a number of challenges. The first one related to technical debt. And this is probably the term that some of you have heard in the context of traditional software systems. When we refer to technical debt, we're typically referring to problems in the code, right? But for deep learning systems, we no longer just have problems in the code. We also might have problems in the data. We may have problems in the models. So the number of issues that we are dealing with significantly increases. Again, remember that this is a typical system that relies on deep learning. 95% of it is packages that are constantly evolving and glue code that pieces it all together, right? This is a real system in deployment. So maintaining such a system becomes a significant challenge. We have problems related to data dependencies. In software systems, we can rely on tools like static analysis, right, to be able to establish dependencies in source code. But unfortunately, we don't have such tools for the data, right? It's much harder to establish dependencies in the data, but this is actually fairly critical for the underlying models, also including all the dependencies to the underlying tools, packages, and infrastructure that we build these systems on. Finally, we are relying on pre-trained models. In many cases, we're just transferring parameters from some other models which have been trained on some other data. So maintaining all that traceability from some other data also poses unique challenges. Finally, we have experimental code paths. So think about this problem as a preprocessor directives in a typical C++ system where you have an enable or disable flag, which may enable or disable functionality. Similar things can and may actually happen in data-driven systems, in this case, deep learning-based system. Configuration management and evolving hardware and software. And as we know, hardware is evolving very rapidly. New GPUs as well as software packaging are creating all these dependencies that have to be constantly monitored so that we can solve these problems effectively. Testing poses one of the most grand challenges in this context, I would say, because in this case, again, we cannot do anything. We cannot test this. We cannot test this system as we are used to testing our typical or traditional software system. Because in traditional software, we can put asserts, we can write test cases. However, we can't just do the same thing in the model code, right? This is a code of a system which is written in TensorFlow, and this is actual instantiation of this architecture, right? So we can't just use control flow or data flow to analyze this model code. We're not going to get anything, right? In order to be actually able to test this system, we have to go into this actual model, into the architecture of the model. We actually have to test this architecture with actual data. So this is what testing means in the context of deep learning-based systems. This is not testing code on the right-hand side. This is actually testing models and the data on the right-hand side. Okay? And we don't have really good ideas for now. Also, understanding these models is very difficult, right? This is what a trained model looks like. And you can imagine millions of numbers here, right? So it's very hard to understand what these hidden layers mean, which features that you represent, and in the context of your question, why that misclassification happened. Which layer is responsible, which feature is responsible for that misclassification, and why, right? So this becomes a very hard problem to track down. Moving to the next question, deployment testing becomes a significant problem because now we need to test not only the model with the data, but we actually need to test the whole deployed system, right? With all the underlying infrastructure and the glue code. And keep in mind that some of the packages, some of the deep learning packages, it relies on are constantly evolving, right? So which creates significant testing challenges as well. Edge case discovery. Sometimes edge cases that we will be running into tomorrow don't even exist today, right? Because we don't have any training data for those edge cases, right? How do we prepare our system to deal with inputs it may encounter tomorrow for which we don't even have training data today? Many of these algorithms are non-deterministic. Obviously creates unique testing challenges, and testing system in production may produce completely different performance results as if we were doing that in-house. Debugging challenges introduces significant challenges as well. Again, let me remind you very quickly how we do debugging in traditional software systems. We can put breakpoints, we can step through the code, and we know how to do that. These are very effective techniques. That's how we find bugs, that's how we fix bugs. However, we cannot just use these debuggers of this code, right? If we try to run debugger on this model on the left-hand side, there is nothing we can't detect any bugs in data or model code this way. We actually have to debug this model, right? But what does it mean to debug this model? Do we put a breakpoint in that neuron, and then when the model stops at that point, we evaluate all those millions of parameters to understand what's happening in the model at that moment in time, right? So obviously, we can't do that manually. We need actually tooling to be able to understand what this particular state means. This just highlights the case that we can't just take traditional debugger technique, slightly tweak it, and suddenly apply it to deep learning systems. We need completely new breed of tools to be able to solve these kind of challenges. Also, lazy executions and underlying packages like distributed TensorFlow, distributed Apache Spark create their own debugging problems. It becomes very hard to debug problems in those deployments. Also, we have bugs not only in the code, we have bugs in the data sets. Some of these bugs can be very abstract when we try to look into those hidden layers and understand why that bug is happening. But also, we have lots of bugs in the model, right? We may have bugs in the model, not just in the data, like things related to non-zero centered activation, dying ReLUs, or vanishing gradient descents. These are all model-related bugs we sometimes have to deal with. Finally, we have deployment challenges. Again, one of them is feedback loop. This is a case where we deploy this deep learning-based system in production, like, for example, a system that predicts housing prices, right? And eventually, customers start making decisions based on the data provided by the system. They start making purchases, and that data gets fed as an input to retrain the system or to update the system. So this may create some unintended feedback loops down the road. Also, some complex data that we're trying to process, or amounts of data may require specialized stream processing algorithms. Also, many of these architectures are distributed deep learning architectures. Also, we're dealing with various data modalities and various data formats that obviously may create additional issues. In addition to this, we also have a number of non-functional requirements related to data safety regulations. For example, recent European Union regulation, which actually requires to anonymize certain data. For us, when we look into a neural network, it's very hard to even understand how it stores the knowledge and where it puts that specific knowledge, right? So now, if we can start thinking about trying to train the network on partially anonymized data, we can't even know what exactly it would be able to learn or how much anonymization can actually impact the learning. We also have a number of organizational issues. This software is built by programmers, data scientists, also front-end people who have different culture, have different processes. Explainability of the models becomes one of the most critical issues, right? So we have no control over how this model is learning features, what kind of features it's able to learn. So sometimes it's borderline ethical to rely on the model without actually knowing how it's able to make certain decisions, right? Especially if we start deploying these systems in mission-critical domains, right? Also, there is a lot of white box and black box module reuse, which is happening nowadays, which also poses its own issues. There are a number of security implications or issues we need to be worried about. There are lots of attacks which have been recently explained on how we can actually hack some of the models, but providing slightly modified inputs that human eye cannot even detect. And there is a lot of research which is actually happening to make these neural networks resilient to these kind of attacks and inputs or malicious inputs. And finally, bias is becoming a big issue. And these systems are relying on training data. And since humans are responsible for, in many cases, creating this data to train these models, sometimes bias becomes just an inherent part of this model. And we don't have really good tools or techniques to be able to actually detect this bias even at training time. Because if we can detect it at training time or at labeling time, it will be too late, right? The model is gonna have parts of its features. Obviously, software engineering research is trying to make some progress towards solving these problems, but there are very, very few attempts. It's really just few approaches, and I just wanted to quickly give you a couple of examples here. So the one is deep test. This approach is basically trying to deal with those cases where we have, for example, deep learning-based network, which is controlling the self-driven car, and it's trying to address that case where the model is actually doing very well until it runs into a situation like this. Like, for example, foggy condition that we didn't have in our training data, and then the model may actually make wrong decision, right? So the question that this paper is trying to address is, how do we make sure that this model has been adequately tested? And second, how do we make sure that we can actually address some of these situations by generating additional training synthetic data to deal with some of these corner cases? And so far, the preliminary results are pretty promising. So they actually applied it on real deep learning-based models, which are used as part of the open competition, and they can actually detect more than 1,000 erroneous behaviors, and they were able to significantly improve the accuracy of the models by generating guided synthetic data. So this idea is actually based on the idea of neuron coverage. So the idea conceptually stems from software engineering notion of coverage, but what they're trying to do, they're trying to measure neuron coverage in the network given the input data. The second paper that I wanted to very briefly highlight is actually trying to help debugging some of the model-based bugs in this neural nets. And again, these are kind of bugs which are extremely difficult to find and detect. So this paper essentially is trying to rely on state differential analysis. So they're trying to identify some of the neurons and features that are likely to be responsible, in this case, for misclassification, right? And they're trying to provide some basic analytical tools to highlight what those features are with respect to the input data, why that particular misclassification happened. So again, much more research is needed in this area, and these are just few quick examples. As I said, software engineering research and machine learning research, I think, have more to do in common than we think, right? Because nowadays we are building these systems that use machine learning. We'll see more and more systems that will have either machine learning or deep learning in them, right? It's going to change the way we are building these systems. So these communities really need to come together to take advantage, first of all, how to refine these processes and how to address some of the challenges that are highlighted. And the other way around, how can we use some of the advances in machine learning and deep learning research to automate some of the software engineering tasks. So with this, I would like to thank National Science Foundation for supporting this research. I would like to thank my PhD students who have been involved in this research. And I would like to open this up for questions. Thank you very much.